Hello everyone dan salam sejahtera. To our fellow partners and speakers, distinguished guests, ladies and gentlemen, viewers, listeners and participants. Welcome to Nanotech Talk 2021 webinar under the Nano Kebangsaan 2021. My name is Amirul Ashraf and I'll be your host for today. For your information, Nano Kebangsaan or NanoKEB 2021 is a partnership program between Nano Malaysia Berhad and National Nanotechnology Centre NNC under the Ministry of Science, Technology and Innovation MOSTI. It is a virtual event that consists of activities which are virtual exhibition, forum, nanotech talk, seminar and many more. NanoKEB event focuses on the nanotechnology development in Malaysia aligned with the National Nanotechnology Policy NNP. NNP consists of 4 strategic levels that will be supported by 15 strategies and 32 initiatives with special focus on the area of energy, agriculture, medicine and electronic devices. The initiative aims to bring Malaysia closer to the aspirations of the National Science, Technology and Innovation Policy to become a high-tech nation by 2030. Our event partners under Nano Kebangsaan are National Nanotechnology Centre NNC, Nano Malaysia Berhad NMB, Malaysia Nanotechnology Association MNA, Sirim Berhad, University Teknologi Mara UiTM, Nano Verify Sendirian Berhad and VSB, University Kebangsaan Malaysia UKM. To begin our webinar this morning, I would like to share a bit information about our webinar. Our session is called Nanotech Talk Webinar, which is a virtual event that consists of Nano Malaysia strategic partners and speakers. Nanotech Talk is a yearly event by Nano Malaysia Berhad that focuses in 4 key strategic sectors. Number 1, electronic devices and system. Number 2, food and agriculture. Number 3, energy and environment. And number 4, wellness, medical and healthcare. Our theme this year aligns with the national initiative in empowering the Industry Revolution 4.0 and the Internet of Nanothing, IO and T. This webinar aims to showcase valuable insights by featuring the nanotechnology, market trends, and issues mainly for industry, companies, startups who would like to venture into nanotechnology and understanding what Nano Malaysia offers. Distinguished guests, ladies and gentlemen, viewers, listeners, and participants, before we start the session, allow me to give a brief introduction about our session today by Engineer Bernard Sagayaraj. Engineer Bernard Sagayaraj holds a bachelor degree with honours in mechanical engineering from University of Malaya, a master's in business administration from Heriot Ward University, and is pursuing his PhD in mechanical engineering at University of Malaya. Mr. Bernard is a member of US Green Building Council, USGBC, and he is one of the earliest leadership in energy and environmental design, LEED, accredited professionals in the country and has a triple LEED accreditation under his belt. Mr. Bernard is the principal of Blue Snow Energy and is currently one of the leading consultants in the country for LEED and energy efficient and air conditioning systems. Without further ado, I will give the floor to Engineer Bernard Sagayaraj, Director of Blue Snow Group, to deliver his presentation about our topic today, which is nanofluids for cooling. Dipersilakan, Mr. Bernard.
Thank you very much, Amirul, for that warm introduction. Let me get on to my slides. Okay, so as Amirul has mentioned, the title is Nanofluids for Cooling. Now, buildings are dynamic entities, right? They're almost like living beings. And in the heart of a modern building is its central air conditioning system. Without central air conditioning system, most buildings, you can't stay inside, especially with weather, high temperatures like this. These central air conditioning systems use water as a heat transfer fluid. The title of my presentation is Cooling with Nanofluids, but then I've also used my title slide to send a message. Now, for those who know air conditioning as a little box in your house, in your room that spews out cool air in the room and is connected to another noisy box outside, which people call split unit. These are different. See the rooftops here, and you see these box contraptions with fans, right? And normally, if you're on a high building, you look down, you see stuff like this. You ever wondered what it was? It's called a cooling tower. And this is, for the lack of a better word, is like the butt end of the central air conditioning system in that building. There is so much more complicated water circuits moving inside. Now, before I get on to nanofluids as a topic, we need to understand what this central cooling system looks like. And what better analogy than using the human body? The human body is a perfect machine, right? You can take any function of the human body, breathing, thinking, moving, and they're all great, actually magnificent. On to blood and blood circulation. Without blood moving in our body, we cease to exist. And what is blood actually, right? What does it do? So, blood is a fluid connective tissue, right? It connects parts of the body together. It's like a circuit that connects your organs in your body, right? It provides the body cells with oxygen, removes carbon dioxide. It transports nutrients and hormones, regulates body temperature, brings waste products to the kidney and the liver, right? Now, this diagram, you know this. I mean, those have done some basic biology. Actually, I've taken that from the encyclopedia, right? So you have fresh blood coming in with oxygen. It goes through a component in the body, and then it comes out to the heart with less oxygen, and so on and so forth. And that's why we live, because of this. And we are familiar with this. This is goes back to the iota, and then the reverse happens. It's a cycle. Look at this on the right side. It's similar, right? You can see the blue and red lines, right? Circuits. Exactly what I show in the boxed area is what happens in a human body and what happens in a central air conditioning system. So in a building that may have dorms, cafeteria, library, gym, the water is flowing all over the place, right? And these are the similarities, right? Let's look at the similarities. As I mentioned, these are what the blood does. But the water in your air conditioning system, your central air conditioning system, does the same thing. It's a fluid connective medium. It transports energy, it transports heat, removes heat from buildings and goes to the cooling towers that I showed in the first slide. And sometimes get contaminated by corrosive elements within the piping systems and needs treatment. Just like if you have problems with your kidney, you need to do dialysis, right? Let's go on to the next slide. Now we talk about the environment, which is a big topic today. And because we are focused on cooling, our focus is also on buildings and city infrastructure. This is actually the hottest area in a country. The cities are the hottest, other than processes, industrial cooling, building and city infrastructure are hot. A lot of energy is consumed. You can look at this graph, and we are moving into the carbon emissions era, Paris Agreement. Energy consumption due to electricity is called Scope 2 emissions, right? And 2/3 of this comes from cooling, and for colder climates is heating. And with the increase in global temperatures, cities that do not normally require cooling are now investing in some form of cooling infrastructure. And although all buildings must be zero carbon to meet the goals of the Paris Agreement, not even 1% of the buildings worldwide are considered net zero carbon today. So how does nanofluid come and help mitigate these issues? Let's go back to a bit of basics. Now, probably have seen this many times on the road. It's the symbol of Audi, the car. But today we're not talking about a car. We're talking about air conditioning systems. But I've made it very simple for you to understand what an air conditioning system, central air conditioning system looks like. by using the ODI as a starting point. That's your room. That's the air in the room. Cool. Warm air gets back into a chill water coil, which is a heat exchanger. Then you have the water circuit that I've been talking about. Goes around. That's a chill water. That goes into evaporator, which is in a chiller. Now, this chiller and all are something that you don't normally see it. It's stuck in a basement somewhere or stuck in a rooftop somewhere. But it is there. It's what giving you the central air conditioning cooling. This is all hidden. And these are the ones that consume a lot of energy. And finally, the heat that is removed from the room now goes into the cooling tower. Remember the cooling tower again. It was in the first slide which I showed you. So this contraption in the yellow box is called a chiller. And normally you don't see it. Now, in a room, closer to the room, somewhere hidden in rooms where you call AHU, air handling units, you have coils like this. And in the evaporator, you have coils like this as well. But I call them coils because they're all the same function. They're heat exchangers. It's within this circuit, which is in this circuit is where you're going to have the nanofluid going in. So remember this diagram, this ODI diagram, where the nanofluid goes in. Now this is another diagram. It's more of like an engineering diagram, but the same illustration. The picture I've shown you here is a chiller. So what you saw earlier in a diagrammatic form in the ODI diagram, this is how the chiller actually looks like. Now, at our firm, Blue Snow Energy, we've been doing research since 2017 on nanofluids, especially using graphene nanoplatelets, GNP. And the whole idea was to use this as a replacement for chill water systems. Our hypothesis was at the time that heat transfer fluid was the final frontier for improving energy efficiency of central cooling plants. Why? Because compressors, chillers, heat exchangers, they have been improving this for years. And you know that at some point in time, it comes down to a sort of plateau. There's so much more you can't do. So that's like the best efficiency would be say 0.5 kilowatt per ton for a chiller, maybe a little bit less. But they also get very expensive. So we asked ourselves, how about if we replace the heat transfer fluid? Today, it is water. What if we replace it with a fluid that has a better heat transfer properties? Hence, the graphene nanofluid. So we have a solution that can assist all cooling or heating systems. And this could either be in chill water or hot water system. Our solution is a graphene nanofluid, as I mentioned earlier. We use 0.1% to 0.5% of the GNP. We use a two-step synthesization process to functionalize it, to move the graphene from being a hydrophobic, which means it doesn't like water, to a hydrophilic group, which means it likes water. Otherwise, you can't mix it, right? It's like if you put Milo and you mix it to make a drink and you keep it for a while, you know the Milo will sediment down, you get water will sediment up, water will stay up. So we can't have that for our heat transfer fluids. So the whole process is made such a way that it's foolproof to sedimentation. Okay. Now we completed our POC, our proof of concept, in 2019, and we got about an average of 32% savings. So this is the little lab that we used in Petaling Jaya to do this. So if you see the graph, this was with water and this was after nanofluids. You can see that the cut in and cut out of the compressor was more, and the area beneath the curve is actually the energy consumed. So you can see that we saved a lot of energy, 32.7%. That's actually a range between 18 to 47%. Now, this year we will be producing nanofluid on a scale-up basis on a commercial rig, and we're testing on a commercial refrigeration rig as well, and we're doing some market validation. And after the scale-up, we will be moving on to the commercialization next year. Okay. How do we carry out the replacement? So in the initial desktop analysis of target plant, we were able to calculate the approximate volume of nanofluid that's required. But before the nanofluid is put into the system, we will carry out a water treatment exercise to flush out, clean away all existing contaminants within the piping system. Once tests confirm that the piping is clean, then we will inject the cooling loop with nanofluid. Okay, and if you look at this diagram for clients who want to confirm the savings obtained, we do a before and after analysis. We call it measurement and verification. So in this case, there's a baseline energy, and moment we have put in the nanofluid, you can see a saving there. We calculate the savings, and then we explain that to the client. When we do all this, we need to understand what will be the value proposition of putting nanofluid inside. What kind of savings we get. This should make monetary value. So in this case, you can see we use a 2,000-ton chill water system. 2,000 ton is equivalent to like a 30 to 40-story commercial building. So we sort of a rough calculation of 60,000 liters of water circulating in the system. We needed to change the 60,000 liters of water with nanofluids. Now, remember I mentioned the savings was about 32.7%. But for our calculation purpose, we just use a conservative 15%. And that alone gives you a savings of 173,000 USD per annum. And that's 2.2 years. And that's pretty good. For most energy efficiency projects, we look at a payback within 2 to 3 years, and that's considered good. Now, that's not the only thing that happens. While we're saving energy, we are also reducing the reliance on the grid emissions, which means fossil fuel. So for Malaysia, we use a grid emissions factor of 0.5 kilogram of CO2e per kilowatt hour. Actually, it's higher than that. It would be, I think it's 0.68 or something, but just being very conservative, 0.5. The carbon reduction based on this 2,000-ton chill water system is about 500 metric tons of CO2e per year. And today, carbon emissions is the talk of the town because of Paris Agreement and the 2030 and 2050 targets. So there is a price to this carbon reduction. And it's at US dollars $50 per ton. And that's another saving of 25,000 per annum the owner gets over and above the energy savings. Now let's move from this to looking at the earth from the outside. These are just Google images, right? Now, why am I showing you this is if you look at the world in the night, those lit up places there are cities. Remember I mentioned cities and infrastructure. These are the ones that consume a lot. But you can see the cities consume so much. Now, we did a quick calculation, right? 2.7% of this Earth's land mass. Forget the sea, just the land mass, right? So 2.7% of the Earth's land mass is about 3.5 million kilometers square. And that is cities. So cities make up 2.7% of the Earth's land mass. Now, this is not a number that we came up ourselves. This is based on a study done in 2010. And the percentage could even be much higher now based on the exponential growth of population since then and, urban migration. Now, if we take 10% of that and say those are actual building footprints, right? Of course, in a building, in a city, there is roads, there's parks, things that are not non-cities, right? Greenery. So if we just take 15%, I say 15% of that is buildings. Okay, and then of the remainder, we assume 50% of the buildings will be air conditioned, right? So we're assuming, taking a broad assumption, so 50% of the buildings in a city will be air conditioned. Actually, it'll be more, right? And this equates to 0.3 million kilometers squared of buildings in cities with air conditioning. And from there, we take 1.5%. That's 4,000 kilometers square of buildings in cities with central air conditioning. Why? Because residential homes don't use central air conditioning; they use split units. But a big building like KLCC or Twin Tower or the Hong Kong Shanghai Tower in Hong Kong, they will use central air conditioning, right? And then we give them some sort of volume. That will be, say, in average buildings about 10 stories. right? We come up with 120 billion meter cube of buildings in cities with central air conditioning around the world, right? Now, 1 ton of refrigeration, RT means refrigerant ton, can cool 40 meter cube. So the global installed base, based on the previous slide, is 3 billion tons of refrigeration. Okay, remember these numbers. An average efficiency of a cooling plant is 1 kilowatt per ton per RT. If you use the simple numbers, so like with the 16 hours of operations, 26 days in a month, 12 months in a year, and we used used the 0.5 emissions factors earlier. By doing this to all the buildings, 7.5 billion tons of CO2e can be removed. Now, if you have, there's a recent book by Bill Gates where it's called How to Avoid a Climate Disaster. He talks about what we need to do to reduce the carbon footprint. We need to remove 51 billion tons of CO2e per year. And this alone, using nanofluids, replacing buildings with nanofluids, can take care of 15% of that problem. That's amazing. Now, what are the other applications? I've spoken a lot about buildings. What are the other applications that seem familiar to you? So we talk about data centers. So now data centers are all now moving towards liquid cooling because server racks are getting more and more compact and they remove a lot and they give out a lot of heat, and air cooling doesn't just cut it. Not anymore. Vehicular cooling. So your electric vehicles have batteries that need to be cooled. Otherwise, they get too hot and they can even explode. So cooling is an integral part of any electric vehicle, not just Tesla, but I'm using Tesla as an example. Process cooling. Process cooling in factories. A lot of industries have a lot of heat and they need to be cooled. And modern air conditioning systems like active chill beams and radiant cooling, these are actually very energy efficient systems, and they use a lot of water. We just replace that water, we put nanofluids inside, those systems get even more efficient. Of course, the big picture that we see are the district cooling plants that are all over the place. In future cities are all going to be combined by one cooling plant. It's going that direction. There are also other interesting future applications. For example, microprocessor cooling, crystal silicon mirror cooling, heat pipes, nuclear power plant cooling, radiator and transformer cooling. So in conclusion, our goal is to get nanofluid into every chilled water system to help buildings and firms reach their net zero energy targets. Thank you very much.
Thank you, Mr. Bernard, on your presentation. To our dear viewers and participants, if there are questions related to our current session today, you may drop your questions together with your email address at the comment section. Our staff is pleased to help you as soon as this session ended. Our viewers and participants, sadly, we have come to an end of our webinar. But before that, I would like to remind that we will have other sessions of Nanotech Talk with more topics that covers by our industry partners, as for example, by Surya Sadanathan, the head of Patent and Industrial Design Department, that will deliver her presentation about intellectual property in nanotechnology perspective, and by TS Dr. Mariam Firdaus, Senior Lecturer UTM and the Managing Director of AM Zaidin's Venture Sendirian Berhad, that will deliver her presentation about quality products start from quality extraction, and by Professor Khalid from Sunway University on his topic related to graphene applications, and by Lux Research, a market research organization which will explain about nanotechnology market in Malaysia and globally, and many more. So stay tuned with us. We would like to thank you for your generous time today. Thank you once again to our partners, speakers, and participants for joining us today. Terima kasih. Stay safe. We'll see you on our next session soon. Bye-bye. Okay. So